Hi, good afternoon, everyone. Welcome to our Connections webinar, fall series number 2. We'll give everyone a couple seconds here to join us this afternoon. Good afternoon, everyone. Welcome. Joining us for our second Our Connections webinar series this fall, focused on academics and our curriculum. Give everyone just another second here to join us. While you're logging in, feel free to pop your name and your location, your class year in the chat feature. Also, if you want to give a shout out to your favorite faculty member, that would be awesome. Always a good way to start our conversation, thinking about some of our favorite Ripon faculty members. Last time we were together, we talked about favorite courses. So let's see what folks have to say. And I'm happy that everyone's able to join us today for the Our Connections webinar, our second version this fall. We have alumni and parents joining us on the webinar to learn more about academics from Vice President and Dean of Faculty John Sisko. And today our special guest is Associate Professor of Physics, Dr. Chris Othon. Remember, we still have 2 more Our Connections series this fall. October 27th, we'll have an economics focus. And November 10th, we'll have a history focus. So stay tuned for more information about those webinars. Again, anytime throughout the webinar, you can use the chat feature to engage with other participants, and you can use the Q&A feature to ask your questions. So let's go ahead and jump right in so we don't waste any of our academic time together. Again, Dean Sisko has joined us recently on campus, so it's great for all of us to get to know him a little bit more, and this has been a fun avenue to do that. It was on the town hall last week if you were able to join for that as well. He's in his month 2 now, and he's the Vice President and Dean of Faculty. Before he came to Ripon, John spent 4 years as the Dean of Colleges of Arts and Sciences and the Wayland H. Cato Jr. School of Education at Queen's University in Charlotte, North Carolina. And prior to that, he has about 20 years of teaching and education administration experience at Temple University, the College of William and Mary, and the College of New Jersey. So plenty of experience bringing here. John got his bachelor's degree in liberal arts from the St. John's College in Annapolis, Maryland, and his PhD in philosophy from Rutgers. Interestingly, and pertinent to today's talk, John is a professor of philosophy, and he's a specialist in ancient Greek cosmology, timely, and specifically a specialist on ancient theories of multiple worlds. So this is going to be a fascinating connection here between the science and the physics of our world and the philosophy behind it. And he's definitely hoping to share a little bit of that with us in the discussion with Dr. Othon today. John's spouse, Karen, is an archivist, and their daughter, Adriana, is finishing up her PhD currently in Women's and Gender Studies at the University of Kentucky. So Dean Sisko, thank you so much for joining us again today. Would you like to introduce Dr. Othon?
Thanks, Amy, my pleasure. Christina Othon was raised in Illinois. She's the first member of her family to graduate from college. She was an undergraduate at the University of Iowa, received her PhD from the University of Nebraska-Lincoln in condensed matter physics. She's conducted research at the National Research Laboratory in Washington, D.C., and at Caltech as well. Her research focuses on how liquid dynamics can modify and regulate biological processes. So her work really does carry over amongst areas of physics, but also biology, chemistry, and medicine. And that really informs her teaching and mentoring of our undergraduate students. This is what we're learning today is drawn from a course that Dr. Othon is teaching right now. And I would actually enjoys painting, crafts, and cooking, and has a passion for gardening. Welcome, Dr. Othon.
Hi, everybody. Thanks for coming today. So I'm going to go ahead and share my screens to give you a brief overview of my Catalyst 120 class and kind of what Catalyst entails and what we're trying to teach our students. So hopefully everybody can see this. So My course is entitled Life and Death in the Universe. And so we talk a lot about the structure of our universe and what we know about our universe, and as well as make some conjecture about whether or not there could be other living systems in the universe. So this relates to the goals of Catalyst 120. So there's lots of different topics that are taught throughout the Catalyst curriculum. And the 120 Catalyst courses emphasize really quantitative reasoning skills. So we're trying to teach students specifically how to make rational arguments and really how to use numerical evidence to help craft stronger arguments. So we really want to empower them to be persuasive. And in particular in this class, they will work on their oral presentations in addition to their written argument making that appears throughout the curriculum. So since this is about making strong rational arguments, I should start by outlining my central claim for, kind of how I establish the this course. And so in my class, what I'm focusing on is formation of strong arguments and supporting them with evidence. So my central claim for my class is that alien life likely exists elsewhere in the universe. However, the vast distances in space and the challenges presented to the development of complex life forms make it unlikely that we're going to detect this life outside of our solar system anytime soon. So that's a very, there's a lot of things that you can challenge in this statement, and you need a lot of evidence to support this claim to make it more than just my personal opinion. And so that's really what we're trying to unpack throughout the course of an entire semester is how are we going to take this open-ended question and break it down into knowable things and teach our students how to gather that evidence to build confidence in such a complex statement. So now I'd like to overview really quickly, I mean, probably too quickly, the evidence needed to unpack this statement. So the first place we need to start is some knowledge of the universe and how big, how vast, that statement of vastness. So I'll start with our Milky Way galaxy. Our Milky Way galaxy contains somewhere between 100 and 250 million other star systems, which is enormous, right? And so we want to give students some sense of scale. So that's where we begin, is building our concepts of scale and how we can articulate large numbers and how we comprehend such vastness. But the Milky Way is only one galaxy in many. And in fact, our local group, so just the nearest neighbors, contain over 80 galaxies, our nearest neighbors. And the observable universe contains 10 trillion galaxies, somewhere between 2 trillion and 10 trillion, which is just an inconceivable number, right? And so we need to build some confidence in this. And this picture that I'm showing here, I'd like to expand. So our first glimpse of the depths of the universe really came from the Hubble Space Telescope, which was put up into orbit around our planet in the early 1990s, and really started giving us some beautiful data about the distant observable galaxies. And so this particular image was made by looking for the most empty piece of space that we knew of. So this is the darkest place in our night sky, and they took a long exposure photo, and you can see that it's just chock full of galaxies. Every single speck of light in this image is an individual galaxy containing hundreds and hundreds of millions of star systems. So it's just mind-boggling. It's huge, right? And this is just a tiny, tiny fraction of the overall night sky. So now that we've established that the universe is huge, let's start to talk about this life thing, right? And the reason that why I think it's unlikely that we're alone out there, okay? So the Drake equation is a famous equation that Frank Drake introduced in 1961 as a way to spur discussion around why we should be looking for intelligent life elsewhere in the universe, right? So this is totally hypothetical. It's just kind of a conversation starter, but it allows us to make reasonable estimates about unknowable things, which I think is such a liberal arts idea, right? You know, like, how do we make reasonable assumptions or reasonable, have an intelligent discussion about things so unknowable, right? So the goal here is to think about the number of technologically communicating civilizations in the Milky Way galaxy. And so all of these parameters are things that I unpack over the course of a semester. And so we start by knowing how the rate of star formation, which we assume to be relatively constant over the last billion years, which is a reasonable assumption. And those are the galaxies available in our past with which are available to communicate. After that, we're gonna start talking about whether or not those star systems have planets, how many of them might be habitable, even if we have a habitable planet, what's the likelihood that life will appear? Even if you have life on that planet, what's the likelihood that it'll be intelligent? And even if it becomes intelligent, how many of those are going to go on to build the technology capable to communicate with another star system? And once you've even accomplished that, how long will you remain able to communicate? So these parameters are all things that we can give data to support and evidence, which is the main goal of Panelists. But you'll see they range from things that we know pretty well, the rate of star formation and fraction of stars with planets, to things that are complete conjecture. Since we are the only intelligent species that we are aware of in the universe, everything on this side becomes quite debatable. That's the nice way to put it. Okay, so why do we think we understand how many of the stars have planets? Is the place that I wanted to kind of begin. The number of known planets to humans has increased dramatically in the last decade and in the last 2 decades, really. So a lot of this data has come from the Kepler Space Telescope. And so I want to give you a brief introduction to this. So prior to 1990, there were no planets that were known outside of our own solar system. And so really, it wasn't until 2014, when Kepler came on, that we started to find planets with a large frequency. And so Kepler really transformed our knowledge of how many planets are out there. So you can see, if I go back, Kepler's field of view is tiny. The Deneb is one constellation that's near the zenith of our evening sky in the winter. And this is just a tiny patch of sky that they have observed, okay? And so they're only observing 530,000 stars. And so far, they have confirmed the existence of over 2,600 planets. They have detected many other suspected planets, but you have to think that this takes a long time. Kepler's only been up there for 9 or 10 years, and a planet has to orbit around in order to be confirmed. And so only the ones that are closest to their central star have been confirmed. All the rest of them that have only transited once, we haven't seen them again, so we can't confirm their existence for another 10 years. Or if you're talking about something like Neptune or Uranus, it's going to be hundreds of years, right? So this is miraculous, actually. It's quite impressive that they've got this many already in just 10 years. So now that we've got thousands of planets, we have to decide how many of those are going to be habitable. Okay, well, habitability comes from our own experience, since we're the only planet that we know that has life. And so here's our star, and it's a prototypical yellow star, a fairly average star in almost every way. And in our, we know the temperature of our star, and our planet actually exists right within the habitable zone of our solar system. And we define the habitability as the habitable zone as the location around which you would find liquid water at the surface of a planet, okay? And so you can see that for a cooler, smaller star, that is going to occur much closer in radius to the central star, and for a larger, hotter star that occurs further away. And so just from knowing, and I teach my students how they can measure the distance to a star, how they know what the star's temperature is, and all these things, we impact that over the course of weeks in our class. So just knowing this amount of information, how can we extrapolate Kepler's data to tell us just how many living civilizations might be out there, or actually how many habitable planets is what we want to know. And so if there's 100 billion stars in our galaxy and more than 1 trillion galaxies in the universe, that would mean that there are 10 to the 23 star systems out there around which there are likely planets. And let's say that we do the kind of skeptical analysis that only stars like our own sun are going to be have habitable planets. That's probably not true, but it kind of gives us a place to start. Well, then that means that there are some 7 times 10 to the 21 stars with planets out there, similar to our own solar system. And Kepler's observations have told us that about a quarter of those have at least one rocky planet in the habitable zone. Okay, so that means that there are 10 to the 20 planets out there that are exactly like Earth. Okay, in the habitable zone, probably, formed with liquid water around stars just like our sun, which is pretty phenomenal, right? And so, so now of all those planets that are habitable, how many of them might have life? This is where we start getting really, really speculative, right? And instead of delving deep into that today, what I wanted to look at was where we might look in our own solar system. Because if we can find life elsewhere that developed independently of Earth in our own solar system, we can basically assume that all 10 to the 20 of those other planets have life, and we just got to go find it. So I'm just going to look at where we should be putting our effort to look for life here in our own solar system. And these are my personal favorites, totally biased, I will be honest. I love this stuff. I love talking about it. In my class, I talk about over 10 of these. I can only give you 4 here, my top 4, okay? So the first one that I really think we should go see is Titan, which is the largest moon of Saturn. And the reason I want to go see this one so bad is because this would be life unlike anything we know about. Because Titan has a really, really dense atmosphere of nitrogen. It has lakes of liquid hydrocarbons and methane, which can be used as an energy source, but it's not water-based like anything we know right now. So we've been there before. We've landed something on that planet to see this and take this data. It's super cold and life would just be so slow. So it's unlikely we would find anything intelligent or anything beyond something that was microbial, but it would be life that is so foreign to us that it's super exciting as a scientist. The next one, and I'm going to talk about the last 3 individually. The next one is Venus. Venus is outside of our habitable zone from what I showed you before, but there's good reason to think we should go back and look for life there. Enceladus is another moon of Saturn. It's my favorite ice moon. There's actually a lot of ice moons, and some of you might be familiar with Europa and others, but this is one of the places where we know liquid water exists in our solar system, and Mars. And so Mars obviously being the closest planet to the one like our own. So Venus may not seem habitable. I mean, it's been described as hell because it has sulfuric acid in its atmosphere, but up in the high atmosphere, it's quite pleasant. So you can see temperatures around 70 degrees that are extremely stable. And there's lots of microbial food sources up there. Sulfur dioxide and carbon monoxide are both food for bacterial animals. And so, and in fact, just last month, okay, this paper was published in Nature Astronomy, and they detected phosphine gas in Venus. And this is kind of crazy because these scientists, all of them worked so hard to come up with any other reason that you would have phosphine except for microbial life, and they failed. They couldn't find any other pathway to create phosphine based upon the chemical resources in Venus and the conditions. And so they just think there might be microbial life floating around up in Venus's atmosphere for us to go check out. So we should definitely go back. It's close. It's an easy mission to plan. We should definitely do it. Okay. So the next one, my favorite, my personal favorite, Enceladus. So Enceladus has a huge ice layer on the outside, but inside it has a giant ocean. It's believed to be salty, and it's warmed by gravitational interactions. We went there in 2005, and we actually took these pictures of geysers that were erupting from the surface of Enceladus and being spewed out into outer space. And we actually flew through it and detected H2. And that was really exciting to people that know biology, because bacteria that live around thermal vents in the bottom of our oceans, they give off this H2, right? So it's associated in our deep oceans and thermal vents with life forms. So we definitely need to go back and see if there's really living systems. This would be life that has been there for probably billions of years. So it could be complex life. And then last but not least is Mars. Mars is so exciting because we know that it once had liquid water on its surface, and it once had a much thicker atmosphere and much warmer temperatures. Even today, during the day, it reaches temperatures close to 70 degrees during the daytime on the surface. And then at the nighttime, it plummets. So it's probably not very hospitable right now, but in the past, it was probably a pretty nice place to be. And we found a lot of evidence which is consistent with organic material, and some people would say microorganisms. And the other reason that we should go back is they have recently detected seasonal methane release. We know methane is basically gas given off by living organisms. And so they are seeing the seasonal variation or the seasonal output of methane, which could be consistent with subsurface microorganisms heating up in the summer and, you know, coming back to life and then going dormant. So there's also some geologic evidence that people point to that looks very much so like microbial mats in ancient oceans on Earth. And so this is very exciting, obviously, you know, totally speculative, but they look similar enough in structure to me to be things that we should go back and test. And then that brings me back to my final take-home message, right? So this is a lovely website that you should all go check out and play with. Actually, informationisbeautiful.net has a lot of visual data. It's a wonderful resource and very fun to play on. And so if you put the numbers in for the optimistic calculations and say how many civilizations are in our galaxy, and you hit calculate, it's going to tell you that there should be about 756 other species, other systems out there for us to communicate within our own galaxy, right? So 756 isn't bad. Definitely, I'll keep listening. Even if you put in the most skeptical results, so you can go over to the tab and click skeptical, that should still lead to about 1 million civilizations in the entire universe. So even with the most skeptical numbers that we can provide you, it's highly unlikely that we're alone in this universe. So that's what I have for you today. A crash course in universe life. So.
Great, thank you. It's just fascinating to start thinking about the vastness of where we live and then the vastness beyond the vastness and how all of this relates. And thank you for sharing so many cool resources and visuals and kind of that data piece. Dean Sisko, do you want to jump to our question in the Q&A as a
Sure.
place?
Yeah. Julian Becker has a question. Is the multiverse theory, and I think it's more of a multi-galaxy theory, a non-falsifiable proposition, given that other universes would be outside of all evidence that we can access?
So the multiverse theory, for those that are not familiar with it, actually suggests that there are entirely separate universes, in addition to just other galaxies. So this is a dimensional question, right? Like they exist, they have are completely separate. Like we would be our own space and time bubble, and then there would be other space and time bubbles elsewhere. And presumably you might even be able to collide and create a new Big Bang in that type of scenario. But there's no way to know. So I view all multiverse and all kind of untestable physics hypotheses, of which there are many, as pure conjecture. If it's untestable and unknowable, it's not really fruitful. That becomes well, John would probably disagree with me there, because that becomes the realm of religion and philosophy, right? Like it's not something that we can verify. It's nothing that I can ever answer for you. So as scientists and as, well, astronomy, the science of astronomy is purely constrained to things which can be tested and made measurements. We are an observational discipline. They don't tend to put a lot of endeavor into things that are unknowable or untestable. So while these are great mathematical models that have really interesting implications for topology and things like that, I don't spend a lot of time on them, because I will never be able to get data from another universe.
That's a great observation. I would say that that's a key difference between ancient cosmology and contemporary cosmology. Since we didn't have Galileo's telescope back in 400 BC, it was really more of a thought experiment proposition, right? What's more likely than not? Is it likely that there'll be many planets or systems out there, and what would preclude that? Together with what we call the principle of plenitude, that if something's possible in infinite time, it must happen, which was very important back for ancient Greek philosophy. One question I had, Dr. Othon, is how important are some of those later calculations, like intelligent life able to communicate to outer space? Might there not be intelligent life that cannot communicate into outer space, yet could be detected by us because of patterns of behavior?
Absolutely. And in fact, there are whole researchers that are developing kind of models on the impact species have on just, the atmosphere. And so even if they couldn't necessarily communicate with us, might we be able to detect them? Certainly, the whole question of intelligence is complex in and of itself. Some people might say that we're the only intelligent species on this planet, and others might say that, no, there's dozens of intelligent species on this planet. We just aren't smart enough to communicate with them. Dolphins and birds have complex thought systems. And where do you draw the line for intelligence? And given enough time, would all of those species end up building telescopes, radio telescopes that could, send signals deep into outer space? Perhaps. So the importance of these, certainly time is one of the variables that we could nail down a lot better. If we go to Enceladus and it's had millions of years and the conditions necessary to build life but didn't, that tells us that life is rare and that we are truly unique. If we go there and get beneath the ice and look down there, and there's just a huge network of civilizations, and they've written books and novels and plays, and we get to go communicate, then it changes everything, right? Because it is orbiting around Saturn, and we would say then that life is everywhere in the universe. So those parameters are really important in kind of answering this question, or kind of nailing down the probability of life elsewhere.
So one of the attendees would like to know about recommendations for further readings on this topic. That's perhaps is something we could communicate, type that into the chat or the question and answer, but is there a book at the top of your head, Dr. Othon, that for the layperson would be a good read?
Oh, so much of what I spent my time is resources for my students, so they're so academic. You know, I'm always looking for an easier textbook that's more dedicated to life and the question of life for this class. And so there is a textbook by Bennett that has some good, it's a textbook though, it's not a layman's fun read. And so I'd have to do a little research on which ones would be good for life in the universe. I am positive they exist, and probably some of the people attending this seminar may know those. But so much of my effort is getting readable content for our student population, and that can really talk about the science of this, that I haven't run across that yet. So.
Yeah, it's interesting. 25 years ago, Carl Sagan was doing a lot with Drake's equation in arguing that, he had these sort of worry about nuclear winter and how our ability to destroy ourselves can impact the outcome of this equation. So there might be something accessible by Carl Sagan floating around out there.
Certainly.
In the chat here. It's interesting.
Chris, I have a question kind of as a follow-up, and I made a note in the chat. I'm happy to get a few details from both of you on things that people may like to read and share that with our participants after the fact, or if any of you know something to share, something you find interesting, definitely happy to share that with everyone for everyone's benefit. The question I had, and it sort of relates back to just Catalyst 120 in general, and right, this is a relatively new thing for our alumni. Obviously, we did not experience this kind of curriculum. And I'm sure we all learned, quantitative analysis and quantitative reasoning when we were here, but what do you find as really a challenge with Catalyst 120, and how do you help students who are not math and science folks and who really don't like math, they have that fear of math, to kind of jump in and learn and feel like they're, getting their college career started in a positive way that will benefit them regardless of their major?
It's such a great question. So most of the students that I teach are not interested in math and science. So I would say over two-thirds of my class are not self-described, science nerds and have a very explicit fear of numbers. And they avoid using numbers in their writing like the plague. I mean, you really have to twist their arm to get them to communicate numbers, because they like kind of these squishy words, is what I like to call them, like less, more, few, and they don't want to make a quantitative comparison because they have a fear of being wrong, right? And we need to teach them that being wrong is not the problem. I mean, you want to be precise and persuasive in your arguments. We have to help them, teach them how to do that. And so I'm constantly reminding them to avoid those squishy words and replace them with concrete ideas, and teach them how to do research, teach them to find things to support their arguments, and then the best way to articulate them. So I keep telling them, is it 3 times more? Is it 4 times more? Is it 1,000,000 times more? Please tell me, what do you mean by more? Like, be more precise in your evidence. And that's the point here that we're trying to make. I have many good writers. They just haven't practiced the skill. You certainly don't learn it in high school. They're not asked to use evidence in the same way. Using citation and resources is one thing, but putting numbers into context and interpreting numbers is a very different skill set. And so I spent a lot of time looking at graphs and asking them what they were trying to convey by creating this graph. Is it effective? Is it, we could do a whole course on data presentation and what makes good data presentation, and poor data presentation. And I'm kind of trying to do all of that within this one semester course.
Great. Yeah, thank you for sharing. I find that super fascinating. And I think an interesting thing for students to try to contemplate is even if you have a career or path that you think doesn't involve data, there's likelihood you're going to have to use data to do something. And how do you translate that?
Right.
And how do you wrap your head around 10 to the 19th power,
Yeah.
right?
What does that really mean?
Right.
What is a mole really, you know?
I missed that. So 10 to the 19th power. So 10 to the 19th is the number of grains of sand on the entire planet.
Oh, well, there you go. That makes good sense now.
Wow.
Yes. So
Active knowledge for the day. That's amazing.
yes, your little
Good trivia question. Good trivia question.
And so I do try to tell students that, you know, we're really, they don't appreciate how often they are presented with numbers until I send them out to look at them. So I send them out to look in their media and everyday life and come back with numerical comparisons. And we get a ton of really fascinating results from that. And, you know, one of the main goals for me personally is to help them avoid quackery or, you know, phishing schemes or other, you know, I guess Ponzi schemes, or just to be intelligent about numbers in their daily life, and so that they really feel empowered to make decisions using data. So
Sure, and then quantification is really quite important. You know, even if it is, some of the wording is squishy, right? So if the advertisement is the Ford Festiva is the only sedan with 5 cup holders and the Ford 5-year warranty. Well, of course, because it's not going to have the Saab warranty or the Toyota warranty, right? It's the Ford warranty.
Yep.
I had a question about observable universe. Is the observable universe a function of the universe expanding and our seeing the edge, or is it a function of our technology or the speed of light, or any of those?
it's the speed of light. So it's a function of the time that we've been in existence and the rate at which information can be transferred to us. So the observable universe is the speed of light times the age of the universe.
Okay,
So
thank you.
you just take the rate at which information can travel, which is the maximum speed of light. What is that? 3 times 10 to the 8 meters per second.
Right.
And you multiply by the age of the universe, which is roughly 14 billion years. And you come up with the size of the observable universe, a radius of 45, what would I put up there? 45 million light years, 45 billion, like, I don't even remember. So,
It was a few, I believe, right?
it's a few, it's big. Sorry.
That's awesome. We saw on the slide that 7 new stars are born each year. How are stars created or born?
Great question.
Short answer to that.
Yeah.
All stars are born out of a cloud of gas, is the easy way to say it. So matter formed in the Big Bang, and then gravity has been pulling that together into larger and larger clouds. And once it reaches kind of a threshold size and density, it starts to collapse more quickly. As they collapse down and start to spin up, they start to heat up. And then at some point you reach a critical density and pressure and temperature, and then a star will ignite, fusion. So stars have formed basically the same way since the beginning of time, and that's just gravitational collapse. And once you pack things tight enough together, you'll get that neutrons start, combining protons and neutrons to form heavier and heavier elements. And then, of course, stars also die, and then they explode and populate our universe with heavier elements, the things that we're made out of, because the early universe only had hydrogen and helium and trace amounts of lithium. And we're all made out of things that are much heavier than that. And that's why I think it was Carl Sagan called us all stardust, right?
Right.
So he, we are all born in the death of a supernova, right? So because our elements are much heavier than those that were created in the Big Bang.
That's awesome. And helium was first detected on the sun. We didn't discover helium on Earth until a later point.
through spectroscopy, which I tell my students all about. So,
Ronald Peterson says, one scientist on how the universe works suggests that the universe is expanding at greater than the speed of light. Any comment?
I don't know about greater than the speed of light. I haven't seen that comment. It's certainly expanding, and it's accelerating in its expansion, which means that eventually, all matter will become separated and cold, and that's kind of the fate of our universe, right? So we do discuss that in my class, the evidence for the expanding universe. The error bars on that data are still enormous. So, maybe we've still got it wrong. Science can be revisionist. We could learn something new about, dark energy or dark matter that changes our current model and our current understanding of that data. Gravity could behave differently at greater distances that affects the data collection. But yes, our current understanding is that the universe is expanding and will continue to expand indefinitely at a faster and faster rate.
And are you saying that with entropy, we could, if thinking about the error bars, put that to the side, we could calculate the time at which the Earth or the universe would be so fully fractured that there wouldn't be life?
Well, space itself is expanding, so that's different than things getting further apart. So because space itself is expanding, the space between the pieces of the atom are getting farther apart. And eventually, it will change everything. I mean, if space it's kind of just going to all get so far separated that chemical bonds can't exist, with any frequency. And there's nothing that's going to be able to overcome the distances of space to bring it back together. And so life and chemistry will stop. Kind of depressing, but yeah.
Well, Amy, you thought we were ending on a high note about 5 minutes ago. I think that's the real high note.
We've maxed it out. We were here and now we've just tanked right down. I think we can end there. That's a great way to stop things, but lots of good questions and discussion. I feel like there's a lot to learn, and look forward to learning more and sharing more. You definitely piqued my interest on a few of these things and thinking about, what's out there and what we don't know. And it is quite fascinating and interesting, even if you're not a scientist or a mathematician, to start to try to formulate and understand what all this means or doesn't mean, or how it's interrelated. And so appreciate you taking the time today to speak with everyone and share your knowledge and information. And Dean Sisko, thanks for moderating once again. We'll have to do it again in a couple weeks. Again, we'll be back together 2 weeks from today for our talk with Dr. Tom Hamami from the economics department. And then 2 weeks after that, November 10th, to hear from Diane Mockridge in the history department. So super excited about the way that we're spending our fall, our Connection series. And I will send an event survey and follow up after the fact, and definitely work on some suggested reading, or at least a few pieces of starting points from Dr. Othon and Dean Sisko to continue the discussion. So thank you all very much, and we'll see you soon.
Thanks, everybody.